So in this lesson, we are going to discuss mathematical modeling. And a mathematical model imitates how a real-world situation works by developing an equation. And it may not fit exactly and be perfect, but the model can be useful in making estimations or predictions. So when you model, you're basically coming up with an equation that resembles the situation. So in real life, a modeling function is never given to us. Most of the time we have to choose the type of modeling function and then go through that process that's called least squares regression to find the actual equation. Now, I'm guessing that most of you have not heard of the term least squares regression before, and so the least squares regression is a statistical procedure that you use to find an equation that best fits data. So if you graph a data set and then you find an equation that comes the closest to all those values, that's what's called the least squares regression method. And when you do this method by hand to find an equation that fits all that data using that least squares regression method, when you do it by hand, it is extremely long and extremely tedious. So rather than put you through that process, I'm going to show you how you can do the least squares regression on the calculator. So before we get into that, though, you have to know some basic, what I like to call the mother functions. And these are functions that have a specific shape that you can use and identify and match with the data to try to find the function that comes closest to the data values. So we have a linear function, that's just a straight line. We have a quadratic and a cubic. Those are polynomials. Quadratic is a polynomial of degree 2, and a cubic is a polynomial of degree 3. Then we have exponential functions, logarithmic functions, and then something called a logistic function, and then a sine function. So I'm going to go through with you what the graphs of these look like. You need to be familiar with the shapes of these functions so that then you can use the shape to decide which function is going to work best for your model that fits the data. So here's the first four. We have a linear function, that's just a line. A quadratic function is going to look, in this example here, it looks like a smile shape where both the arrows are pointing up. You could also have a quadratic that has that same shape, but it's flipped upside down, so then it looks like it's a frown shape. So anything that looks like a smile or a frown shape can maybe be modeled by a quadratic. Then you have a cubic function, which starts in one quadrant and kind of ends up like in the diagonal quadrant. And it has a smooth curve to it. And then you have the exponential function. The exponential function in this particular graph is increasing because if I trace it going left to right, it goes up. You could also have a decreasing exponential function, which basically is if I flip it over the y-axis and it goes down left to right. So you could have an increasing or decreasing exponential, but either way, it's going to flatten out at one end and jump up really high on the other end. A logarithmic function is going to have a shape where on one side, it goes down really fast, and then on the other side of the function, if you follow the arrow to the right, it's going to increase slowly. A logistic function is flatter on one side, and then as you trace it left to right, it's going to go up faster in the middle, and then it's going to start to flatten out. It's still going to increase, but it's going to increase more slowly as you go further along the curve. And then the sine function, I didn't draw it symmetrically. This should be a symmetric function. I have horrible drawing skills. But this is just a cyclical function where it just keeps repeating over and over again. So sine would be a really good model for something like temperature during the day because it's going to repeat over and over and over again, where you start off in the morning where it's cooler, then it gets hotter through the day, and then as it gets nighttime, it goes down and it decreases again, and then it repeats. So that might be a good example of where you might use the sine function. So those are some basic shapes you should be familiar with. Now, here are the steps on how to model. This will take you through the process of modeling. So the first step is to identify the independent and dependent variables. Now, the independent variable is the variable that you'll put on the x-axis or the horizontal axis, and the dependent variable is going to be the variable that you put on the y-axis or the vertical axis. And you want to make sure whatever you put on the vertical axis for your y-axis, that's definitely got to be the dependent variable. And a dependent variable is what you're measuring in the experiment. What is affected during the experiment? So the dependent variable responds to the independent variable. So it's called the dependent variable because it depends on the independent variable. So, for example, going back to the temperature idea, the temperature is what we're measuring, so that would go on the vertical axis for the y value, and then the hours in the day would go on the horizontal axis. And the dependent variable is the temperature because the temperature is going to depend on the time of the day. It's going to change based on the time, right? It's going to be cooler in the morning, hotter in the afternoon, and then cooler down, and then cool down at night. So the dependent variable is the variable that depends on whatever the other variable is. Okay, so first you have to decide what's the independent and dependent variables in the situation. Then step 2, you're going to graph the data on your calculator, and then you're going to determine the best mother function that fits the data. So when you graph the data, you look at the shape of the data. It's not going to be exact. Most of the time in real life, you're not going to get something that fits exactly. Life is messy. It's never going to be perfect. However, you're going to try to determine what shape would be closest to the shape of the data. Then once you figure out what kind of function you want to use, then step 3, you're going to determine the domain for your model that will make the most sense. And then step 4, you're going to use the calculator to perform least squares regression and determine the equation that best fits the data. So that's the part, step 4. If you were doing it by hand, it would be long and messy. But in step 4, I'm going to show you how to do this on the calculator to save you some time. And then make sure when you write down your equation, you have to make sure that you label and identify your variables. Step 5, we're going to determine the value of r squared and interpret its meaning. And r squared, and I'll go through this in more detail in just a minute, r squared is going to give us an indicator of how the model fits. Is it a good fit, a bad fit? Is it an okay fit? The value of r squared will help us determine if it's a good fit or not. And then step 6, if you have a question you're trying to answer, which is probably the whole reason why you're doing this, you use your equation to answer the question. So the equation is usually going to help you make a prediction or some kind of estimation. And then you want to look, does my answer make sense? Okay, so what is r squared? We're going to get the value of r squared from your calculator. You don't have to worry about calculating this. But r squared is a statistical measure on how close the data is fit with that regression curve. So sometimes it's also known as the coefficient of determination. And r squared tells us the percentage of prediction error in the y variable. What percentage is eliminated when we use that least squares regression on the x variable? So the higher that r squared value is, the better it is, because we want to eliminate as much of the error as possible. And r squared is always going to fall, because it's a percentage, it's always going to fall between 0 and 100%. Now the calculator gives it to you as a decimal. So for example, if the calculator tells you that r squared is 0.65, that represents 65%. So just keep that in mind, that r squared on the calculator is going to be given to you as a decimal, and then you can change it to a percentage. And we want to make sure, and I'm going to show you how to do this, you want to make sure that your diagnostics on the calculator are turned on so that you get that value of r squared when you go through this process. So to make sure your calculator is set up so that you can determine the value of R squared, the first thing you're going to do is go to your catalog in the calculator. So your catalog, you'll see, is listed right above your 0 button. It will say in a different colored catalog. So you're going to hit the second button and then the 0 button, and that will access your catalog. And your catalog is basically that lists all your functions and commands in the entire calculator in one list. And it's listed in alphabetical order, like an index when you look something up in a book. So we want to scroll down to the D's, and we want to look for a command that's called diagnostic on. Okay, when you have your little arrow highlighted on diagnostic on, you want to hit the enter button. And then you want to hit the enter button one more time and it should say done. So now your calculator is set up so that when you go through the process of regression on your calculator, it will give you the value of R squared. So we're going to walk through 3 examples. The first example is about modeling atmospheric pressure. So the information that's given is the altitude in meters and then the pressure in millibars. So as you can see that as the altitude increases, we go from 0 to 5,000 meters to 10,000 meters to 15,000 meters, etc. So as the altitude increases, look what happens to the atmospheric pressure. It decreases. So it goes down. So it starts at about 1,000, a little over 1,000, and it starts to go down pretty rapidly. So the first step is to determine what the independent and dependent variables are. Now, since the air pressure depends on the altitude, we are going to say in step 1 that the independent variable is the altitude and the dependent variable is the pressure in millibars, because the pressure is changing based on the altitude. Okay, the second thing we need to do is graph the data and determine a function. So let's pull up our calculator and I'll walk you through the process on how you can graph and how you can create a scatter plot. So the first thing we need to do to make a scatter plot is to put our data in our lists. So we're going to do that by hitting the stat button. And then we're going to choose the edit option. And you need to enter your X values in L1 and put your Y values in L2. So when you look at the chart, your X values, because we chose this to be our independent variable, our X values are going to be 0, 5,000, 10,000, 15,000, etc. And then in L2, we're going to put our Y values, which was the pressure in millibars, which starts with 1,013, 541, 265, etc. So you want to make sure you put those into your list, L1 and L2. Now, you also want to verify that your X and Y values match up or this isn't going to work. So, for example, when you look at the chart, the millibars that's matched up with 10,000 should be 265. So when I look at my L1 and L2 for 10,000, I should have 265. So you want to make sure that the X's are corresponding to the correct value of Y. Once you put your data in there, then you're going to access your stat plot by hitting second Y equals. Above your Y equals button, you can see it's in a different color. It's labeled stat plot. So you hit second Y equals. Now you want to make sure that all of your stat plots say off except for the one that you're using, and that way you don't get any interference from any other graph. So I'm going to choose plot number 1 because that one's on and all the other ones are off. I want to make sure that it's highlighted on. I also want to make sure that for the type, it's the first option that's a scatter plot. And then because I put my x's in L1 and my y's in L2, I want to make sure that those values correspond to X list and Y list. Now, if you need to change that and you forget where your L1 and L2 values are, your L1 is above the 1 button and your L2 is above the 2 button. So you have to hit second 1 or second 2. Then the mark and the color is preference only. It's not mandatory that you change those. The mark is just going to be the mark that's going to display for each of the points. And then if you have a choice, you can pick your own color. Now, once we have everything set up the way we want it, then to graph it, we're going to hit the zoom button. And we're going to use zoom number 9, zoom stat. And what that does is by choosing that zoom number 9, it automatically fixed the window for us. So I'm going to choose zoom 9, and then it will show me my scatter plot. Now, when I'm looking at this, this looks like an exponential function to me, like a decreasing exponential function to me, because it's flattening out on one side and it's going up rapidly on the other. So as I look at the graph, left to right is going down. That shape to me is a decreasing exponential function. So that is going to be my choice when I go to choose my mother function so that I can do the procedure that's called least squares regression. That is my mother function that I'm going to use. Since the person that collected the data went from 0 to 30,000 meters, let's stick with that for the domain. I can't imagine anything being much higher than that. I know Mount Everest is about 29,000 feet, which would be probably about, I think, close to 9,000 meters. So 30,000 is way up there. All right, now let's actually find the equation for this. Now, to do that, you want to hit the stat button. And then across the top, there's 3 menus. There's the edit menu, the calculate menu, and the test menu. You want the calculate menu, so I'm going to arrow over. Now, under here, you have all kinds of regression. So starting at number 4, we have linear regression, we have quadratic regression, we have cubic regression. Then let's see, we have number 9 is logarithmic regression. And then what we're looking for, since we picked an exponential function to model this data, we're going to use option 0 that says exponential regression. So I'm going to hit enter on that. Then I want to make sure that my X list and my Y list match up. So I have my X's in L1 and my Y's in L2. So make sure those say L1 and L2. Skip over where it says frequency list. Store regression equation, that's optional, but I highly recommend it. It's very helpful because what's going to happen is when you get your equation, most of the time you're going to have a lot of decimal places, and this will give you the option to store your equation without having to retype all those digits in. So I'm going to tell it to store it under Y1. So in order to do that, I'm going to access my F4 function key. Right above trace, it says F4. So I have to hit my alpha button first to access that F4. So I'm going to hit alpha trace. So you can choose any of these equations to plug them into, but I usually just use Y1. So I'm going to hit enter. And then I'm going to arrow down and I'm going to hit calculate. And so there is my equation. Now, some of you may have a different version of this calculator where you have to go about this a little bit differently. Most of the steps are the same until you get to where you hit exponential regression. So if you get to that point and it shows something different on your screen, look at that supplemental video that I put in the instructions. That will show you how to do the regression on your calculator. Then if you go to y equals, you can see that it put the equation in there for you. Now when I hit my graph button again, it will show you my data and the curve that we picked. So you can see that this curve, this exponential function, fixed the data very well. Now that we have our model and we've gone through that process, we can say what our equation is. If you look above in the top line of our calculator, it has the general form of the equation, y equals a times b to the power of x. So we're just going to insert those numbers into a and b. So it says a is 1104.92, and you can put in all those digits, and then b is 0.99985, etc. You can put in all those digits. So you substitute those in for a and b, and then you have your equation. And since we said that the independent variable was going to be elevations in meters, and the dependent is going to be the air pressure in millibars, we can identify that x is going to be the elevation in meters, and y is going to be the air pressure in millibars. Now, it says that r squared is 0.998997. That is super close to 100%. That is like almost perfect. So that tells us that we have eliminated about 99.9% of the prediction error of the air pressure. And that's by using the least squares regression method. So that is a really good model. The closer you are to 100%, the better the model is. Now, when we graph our model with the data values, we can see how close that curve of our equation fits the data. It's almost perfect. So it kind of matches what our value of r squared is saying. It's a really good fit. So now in step 6, if we want to predict the pressure at an altitude of 23,000, that should be meters. You can cross that off and fix meters. If we had an altitude of 23,000 meters, we can use our model. So we would plug in 23,000 into our function for x and figure out what our value of y is, which is the pressure in millibars. So when we plug in 23,000 in for x, we get about 35.1 millibars. Let's look at example 2. It says one of the earliest studies about population growth was done using yeast plants in 1913. A small amount of yeast was placed in a container with a fixed amount of nourishment. The units of yeast were recorded every 2 hours. So in the table, you see the value of time in the top row and then the number of units of yeast in the bottom row. So when we look at this, for example, after 6 hours have passed, there's 174.6 units of yeast. So the first step is to determine the independent and dependent variables. Because the yeast is growing based on the number of hours that have passed, we're going to say that the independent variable is time and the dependent variable is the units of yeast. The units of yeast is going to depend on how much time has passed. So now let's go ahead for step 2 and graph the data. Let's enter in our data. So to do that, we're going to hit the Stat button, then go to Edit. And to clear out my list from the previous example, I'm going to go up to L1, make sure it's highlighted, and then I'm going to hit Clear, Enter. And I'm going to go over to L2, make sure it's highlighted on L2, and hit Clear and Enter. Now I can go ahead and enter in my values. So under time, it's every 2 hours. So I'm going to just put in 0, 2, 4, 6, all the way up to 18. Then I'm going to go over and put in my Y values. Be careful to make sure you're entering everything in correctly. Go slow and double check everything because it's easy to mistype something when you're punching in a lot of data. I do it myself all the time. Okay, once you have everything in there, You don't have to mess with the stat plot anymore because we already set it up from the previous example. So what I would do is just go in and clear out any equations that you have in your y equals. So hit the y equals button, clear it out because you don't want that interfering with your graph. And then to graph the data, you're going to hit zoom and then option number 9, which is your stat plot. And then there's our picture. So looking at that graph, and I look and compare it to my mother functions, this to me looks like a logistic function. So that is what we will use when we perform least squares regression. So in step 2, we graph the data and determine the mother function. Because the graph had a shape that looked like a logistic function, that's what we're going to use. And because our chart goes up to 18, we can make the domain 0 to 18, but I'm going to go a little bit further out to 20 just to make it a nice even number. And then if we want to try to make any predictions past 18, it's not too far away from the data where we can make a good guess. So I'm going to make the domain 0 to 20. Now let's perform least squares regression. Find the equation that fits this data. We're going to go to the stat button. And now we're going to arrow over to the calculate menu. And I want to scroll down and look for logistic regression. Logistic regression right here on menu option B. So I'm going to hit enter. I'm going to tell it to do logistic regression on L1 and L2. I'm going to skip over frequency list and then I'm going to go to store my equation. So I'm going to choose F4 by hitting alpha trace. Then I'm going to tell it to store my equation in Y1. And then I'm going to go down and tell the calculator to calculate this equation for me. Now it's figuring it out. And there it is. So we have a fairly complicated equation here. If you look up here, it has y equals c all divided by, and then in the denominator we have 1 plus a times e to the power of negative bx. So what we have to do is plug in our values for a, b, and c in here to get our equation. Okay, now we have our equation. So let's go to step 4. We're going to plug in our values and we're going to write our equation. Remember, C is what goes on top. If you look at our general form of this equation, we have y is equal to C on top and then 1 plus a times e to the power of negative bx. So C, which is 661.8, that's going to go on the top here. Then in the denominator, we have 1 plus a, which is 74.46 times e to the power of negative 0.552x. Now, remember our x is our independent variable, and we said that that was time in hours, and y was our dependent variable, which we said was the units of yeast. And for step 5, we usually look at our value of r squared, but for logistic functions, the calculator doesn't do r squared. So we're going to skip that part whenever we do logistic functions. Now that we have our equation, we can graph the data and the equation together by hitting the graph button. And we can see that that's a really good fit. It looks perfect. It looks like every single point is on that curve. Now that's not typical in real life. These examples I pulled from a book to walk through with you. And typically the data in real life does not fit curves that nicely. Now that we have found the equation and we've graphed it with our data, we can take a look at what that looks like here. And we can see from the graph that this is an excellent fit. All of those points are like right on that line. So now for step number 6, we're going to use our equation to estimate the number of units of yeast at 7 hours. And so we don't have the information for 7 hours. Remember, it gave it to us in multiples of 2. So we have the information that was collected for 6 hours and for 8 hours. But if we want to estimate what happens at 7 hours, we can use our equation. Since x represented the number of hours, I'm going to plug 7 in for x into that equation, and I'm going to get 258.19155 units of yeast. You can plug that in on your calculator. So we're going to go back to the home page, and we're going to do that by exiting and quitting out of the graph area. So right above the mode button is the quit option. So I'm going to hit second mode, and that brings me back to my home screen. So to plug in 7 into our function, I'm going to click 661.8. That's in the numerator of our fraction. Then I'm going to divide by, and then I need to put in parentheses all that stuff that's in the denominator. And the parentheses is important to make sure the calculator understands that all of what's inside the parentheses is in the denominator of that fraction. So I'm going to put 1 plus 74.46. And now to access our natural exponential function that's represented by that e, right up next to your 4 button, there's a button that says ln for logarithms. And then right above that, it says e to the power of x. So I'm going to access that natural exponential function by hitting the second button and then the natural log. So I'm going to hit second, log, and then I have, it automatically puts the e in there, and then I put in my exponent. So I'm going to put in negative. Make sure you use negative, not the minus, because otherwise it will yell at you and give you an error message. So I'm going to put in negative 0.552, and then where the x is going to go, I'm going to put in times 7, because we want to figure out what this is at 7. Now, to drop back down out of the exponent, I'm just going to use my arrow button to push right, and it's going to drop it back down, and then I can close my parentheses. So this is what it should look like when you enter this in on your calculator. Then I'm going to hit enter when I verify that everything looks good, and it should give me 258.267357, and that's units of yeast. Okay, we have our last example. We're going to talk about highway design. The problem reads, to allow enough distance for cars to pass on a 2-lane highway, engineers calculate minimum sight distances between curves and hills. The table shows the minimum sight distance, y in feet, for a car traveling X miles per hour. So X represents the speed in miles per hour, and y represents the distance needed to see when you're going at a particular speed and you're trying to change lanes. So step 1, we need to determine the independent and dependent variables. Because the distance you need to see in order to change lanes is dependent upon your speed in miles per hour, we are going to say that the independent variable is the speed, while the dependent variable, the distance in feet for the sight distance. So the next step, we're going to graph the data to determine what function we need to use. And enter the data. I'm going to go to the Stat button, and then I'm going to choose Edit so I can go in and put my L1 values and my L2 values in there. To clear out the list from the previous example, I'm going to make sure I'm highlighted on L1, and then I'm going to hit Clear, Enter. Then the same thing for L2. I'm going to make sure I'm highlighted on L2 and then hit Clear, Enter. Since we decided that the independent variable, which is going to be our x's, is going to be the miles per hour, I'm going to put all the values in my list 1. Then for list 2, I'm going to put in the feet and distance for the sight distance. And I want to make sure that I'm checking it as I put it in, that my X's and Y's are corresponding as they are on the table. And I'm making sure that I'm going slow enough that I'm not going to make a typo, although it still will occasionally happen. But if you take your time and check it as you go along, you'll minimize the chance of that happening. Okay, now to graph our values, we have our stat plot already set up from the previous example. So I'm just going to go straight ahead and push zoom number 9. And it looks like I forgot to clear out my y equals. So let me do that. I'm going to hit y equals. I'm going to clear out our function from our previous example. Now when I go back to zoom 9, I don't see that line at the bottom and it won't interfere with my graph. Okay, when I'm looking at those data values, it looks pretty close to a linear function. It looks like a line. It's not going to be a perfectly straight line because data never is perfect, but it looks pretty darn close to being linear. So I think a linear function would be a good model for this data. So now we have our graph and we know that we're going to use a linear function to model this data. The next step is to determine a reasonable domain. Since most highways have a speed limit at most 75, I'm going to set my domain from 0 to 75. Now let's go ahead and do step 4, perform our regression and find our equation. So to perform linear regression, I'm going to go to Stat, and then I'm going to arrow over to my Calculate menu. And now I'm looking for linear regression, so I'm going to scroll down to option number 4. I'm going to hit Enter. I know that my X's are in L1 and my Y is in L2, so I'm good there. I don't have to make any adjustments. So I'm going to go down to store our equation, and I'm going to tell the calculator to store my equation in Y1. And then I'm going to tell it to calculate my line. So there's my line. I have y equals ax plus b. A is 34.679. B is 48.925. And our r squared is 0.987244. So let's go ahead and put that on our information in step 4. We have our information to set up our equation. When we plug those values in for a and b into our equation, we're going to get that y is equal to 34.679x plus 48.925, and that's when we round to 3 places. And remember that x represents the miles per hour, which is our speed limit, and then y is the sight distance in feet. So step 5, we didn't do that in the last example because the calculator doesn't do that for logistic functions. But in this function, we can recognize that there's an r squared value. And the r squared is given to be 0.98724, etc. And this means that if we multiply by 100 and put it in percent form, this means that about 98.7% of the prediction error of the sight distance is eliminated by using least squares regression. Now to graph the data and the line at the same time, I hit zoom 9, and because I stored my line in my y equals, it's going to now graph it. So I can see that this isn't an exact model, which it never will be in real life. But it's pretty darn close, and there's our data and our line together. If I go and look at my y equals, there is my regression line all in there with all of the digits. So now that we have looked at our function and we looked at it with the data and we saw that it was a pretty good fit. It's not perfect, but it's a really good fit. For step 6, if I want to estimate the speed limit, if the sight distance is 950 feet, we can use our model to do that. Now remember, our sight distance represented the y value. So I'm going to put 950 feet in for y, and then I'm going to solve for the speed limit, which is x. So when I subtract 48.925 from both sides, and then I divide both sides by 34.679, I'm going to get that there's a speed limit of 25.98 miles per hour. So once you set up your equation, just in general, when we're looking at mathematical modeling, after we set up our equation, we can use that equation to make estimations and predictions. And that is really the main idea of mathematical modeling, is to come up with some kind of equation that represents a real world application or real world event so that we can use that equation to make estimations and predictions.